Hi, let's talk about paging and how you can use any virtual memory address to get a bunch of different information about that memory. And so basically, to describe paging is a procedure that operating systems use to help map virtual memory addresses to physical memory addresses. So imagine you have a box like this of all of your memory, and you divide it into equal pages like this. So in this case, we have pages 0 to 5. They're all equal sizes, so no page is greater than another. And one page could be OS stuff, and then this one could be a process, this could be a process, this one could be empty, this one could be a process, and so on and so forth. And so I'm not going to get into the details of how you can size the pages to achieve efficiency or anything like that. I'm just going to go over how you can take a memory address like this and get information from it. So let's say you have a sample memory address that looks something like this. So it's 32 bits long, which means that we're dealing with 4 gigabytes of memory maximum. We're dealing with a 4 gigabyte system, and our page size, the size of our pages is 8 kilobytes. What we can get from that, 8 kilobytes is equal to 2 to the 13 bytes. 2 to the 13 bytes. Now, we can immediately get two numbers from this. So for one thing, the page offset bits is 13, which refers to this exponent right here. The page offset refers to where in the page are we going. So it's these bits right here. So I'm going to color them blue. And so it's saying here's whatever page I'm accessing. And now this is the memory within that page, within that 8 kilobytes that I want to access. That's the page offset. Now, we can also calculate the VPN bits. Now, I'm not talking about a virtual private network, ExpressVPN, or NordVPN, or Global Protect. Oh man. I'm talking about a virtual page number. And so the amount of bits reserved for that is easy to calculate. It's the total number of bits, which is 32, minus the page offset bits, which is equal to 19. And the same is true for page offset bits. It's going to be 32 minus 19 equals 13. So they're both the same in that way. So we can color this part. This is our page number, our virtual page number, red. So this is the page number, and this is the offset within that page. That's a good way to understand it. Now we can easily get the number of pages, or also the number of page table entries. They're basically equivalent. And that's just going to be an easy calculation. That's just 2 to the exponent of our page number bits, which since there's 19 bits, there's 2 to the 19 different combinations. Now that's some large number. That's like 500,000 or something like that. The next thing is for a page table entry size. Now, from what I saw, this is by standard 4 bytes by most systems, but you can change this, but for this, we're going to assume it's 4 bytes. We can use that to get the page table size, which is just going to be conveniently the number of pages multiplied by the entry size. So that's going to look like the number of pages we just calculated is 2 to the 19. Multiply that by our 4 bytes, which is also equal to 2 to the 2, which is going to be 2 to the 19 plus 2. That's exponent laws, which is equal to 2 to the 21, which is about 2 megabytes. Oh man, I ran out of scroll. There we go. So that's our page table size. And so just from this, we were able to calculate all of this, while also knowing this as well. It's also worth noting that so far I've been describing single level linear page tables, but some operating systems will do a multi-level page table, which looks something like this. A multi-level tree structured page table. In this case, it looks like 2 levels. So instead of dividing your memory like this, where you have all of your memory and you're dividing it into pages of memory, like that, instead you're going to divide all of your memory into pages of page tables. So each page basically has its own page table. That's a way of thinking about it. And so let's take that same sample address. This is the same one we copied above. Same exact calculations that we made from above, and we're going to use it to calculate some more information. So first, let's calculate the number of pages within that page table. So basically, I forgot to erase that. but that comes later. So basically, the number of pages in the page table, we're thinking this page table, which we're going to conveniently call page directory. So I could also rename this and say number of pages in page directory is going to be basically, we're dividing the size of the page table. So I'm going to call it page table size by whatever the size of our pages is. So a page size, which basically is going to look like this. So our page table is 2 to the 21. The page size is 2 to the 13 because it's 8 kilobytes, which looks like 2 to the 21 minus 13 following exponent laws, which equals 2 to the 8, which equals 256. So that's the number of pages in our page directory. And so notice this 8, that exponent is very useful because that tells us the number of bits in our page directory index. So this is like which page directory, which page table are we accessing here? That's what that's asking. And so that's 8 bits. Now, how many pages are in each page? Well, that's basically asking how many pages are in each one of these page tables. And so to calculate that, we're basically going to take the number of pages. So the number of pages, I forgot to copy it, but we calculated it up here as 2 to the 19. And we're going to divide that by the number of pages in the page directory, so it's going to be 2 to the 19 divided by 2 to the 8, which is going to be 2 to the 19 minus 8, which is equal to 2 to the 11, which should be equal to 2048. Oop, there we go. And so this 11 is going to refer to the page table index bits. And so I'm going to do something. I'm going to color this orange, and I'll color this red so we can visualize it in our sample. So right up here, it's going to be the same kind of process. This is our page directory index. So I'm going to make it orange. This is our page directory index saying which page table are we going to use? And this is the page number within that page table, which has 11 bits. And so that is all of our calculations. Thank you for watching. Have a good day.